The other one we spent some time on was developing barrier templates. There are some in here that probably shouldn't have been loaded in. However, the ones that I encourage use is especially if bridge ends up modeling approach slabs for road, this 32-inch F-shape approach left final, that's the name of the template. The only difference between this and the 32-inch left shape final is this chamfer right down here. So on the thin deck or the approach slab, wherever on a bridge, 32-inch F-shaped bridge rail, you'll have the deck chamfer right there, and it'll attach to the bridge deck right at the top of that chamfer. I also set up the approach left final because the approach bridge deck does not have that chamfer, and so we made the bridge rail also not have that chamfer so that you can apply it right at the edge of the approach slab. And then each one of these has at least one variable constraint, which allows the bottom of the template to be sloped up at the cross slope of the shoulder. If I can briefly go through this, 0.8, I'm going to apply shoulder left 1, that's what I named it. The bridge rails don't let you apply the super elevation automatically. There's no super elevation checkbox here. But you can go in and define whatever your shoulder slope is. You can define that for the bottom of your slab, or bottom of your bridge rail. So 0.8 will rise or fall based on that slope. And then if you look, 0.7 is based off of 0.8, so that'll always stay the specified distance. I think it's 5 inches, 3 inches, 3 inches from 0.8, and it's set at 1.25 feet from the working point. So it's 1.25 horizontal, it's 3 inches up from 0.8. And then all of the other points are defined horizontally from the previous point until you reach up here at 0.5. So those are all based off of wherever 0.8 ends up at, so that you can eventually define that 0.5 is 32 inches vertical from wherever 0.8 is. 0.4 is based off of 0.5, so it's going to be flat level. 0.3 is then where we're back to defining it from the working point from here, because that really doesn't need to be adjusted based on where the cross slope ends up putting 0.8. So 0.1, 0.2, 0.3 are all defined off of the working point, but the ultimate goal was just to make sure that we've got the 32 inches vertical from 0.8 up to 0.5. And we did that on both left and right for 32 and 42 inch bridge rails. The other nice thing about the 42 inch bridge rail, you can see the 10 inch section that's applied here, and that is, so it's the 32 inch bridge rail, so 0.8 is still defined off of where 0.11 ends up, 32 inches up, and then 0.7 is actually a variable constraint so that you can define this bridge rail as being 32 inches tall, transition up to a 42-inch tall deck or bridge rail to a certain station, transition back down to a 32-inch bridge rail. If there is a bridge, curved alignment, whatever it is, that the 42-inch shape will be from EWS to EWS, then that variable constraint just can stay right where it's at the 0.83 feet and not have to be transitioned at all. The other thing that I wanted to briefly talk about, whatever your master unit, subunit are set at, anything that I go in to modify, so these start values, end values for this variable constraint, well, it's in decimal feet. However, that is only because the master units for the design file are set to decimal feet. If I go in and I change that to feet inches, then I will need to enter everything in to my start and end values as feet and inches. It's going to be personal preference, whichever way you prefer, but I do prefer the feet inches because it's a lot easier to remember, a lot easier to type out 0 feet, 0.25 inches than it is to approximate that with the 0.002 feet. So just wanted to touch on that briefly, that this is not stuck to decimal feet. If you prefer feet inches, which most of the time that's what I was using in MicroStation, that's what I'm familiar with, that's what I'm comfortable with. Okay, so that is kind of the basics with whether you want decimal feet or feet inches entry throughout building your bridge model. It does cover just a little bit of the templates. I still believe that there are the K1, K2, K3, or I'm sorry, K2, K2 plus 1, K3, K3 plus 1 plus 2. I had attempted to go in here and instead of defining each one of these as a K3 plus 2, K3 plus 1, I tried coming in and having K3, just the K3 base, and then making my top points here, P1 and P0, or technically P2 and P11, as variable constraints. And I just could not figure out how to set those during beam placement. So I only had to set them one time. What I ended up having to do is select each beam and go into the variable constraint and set it, in this case, P11 and P2. In order to get a +1 beam, I had to define it as -1, so that the distance between P0, P11 increased by an inch. But I had to do it for each beam, so it made it very obnoxious to have to do it that way. So instead, we just went through and made the templates. There's got to be a way to define that constraint at the time of placement. Maybe Connect has made that a little more clear. For the time being, anyway, you've got all the K-beams and at least the basis of the NU girders at the +1 that KDOT requires. It will require just a little bit of work in order to get the NU 35 plus 2, 43 plus 2, etc. Or figure out how to make that constraint work in your favor. That would take a little more time on the NU section. those are what I'm talking about when I'm talking templates, and also when I'm talking about constraints. There are pre-built templates and these are mostly templates that were put together before we knew enough about OpenBridgeModeler in order to really make the templates start working for us. So there are a lot of examples of hammerheads, McPiers, multi-column vents. There's a whole lot of them, and I believe that developing templates, developing very broad-based templates in order to speed along this process is only going to help things along. So again, thanks. I will get on to the next video.